Hello students, welcome to Educate. We are going to continue with chapter waves of class 11th physics. So in previous lecture we have studied up to Laplace correction. Now we will continue. So next point is the principle of superposition of waves, means when two waves superpose, then a resulting wave is obtained. That may be standing wave or progressive wave, that depends, right? So here the resulting wave y as a function of xt will be equal to y1 as a function of xt plus y2 as a function of xt. Now here waves can be written as like y1 is f1 x minus vt, y2 can be written as f2 x minus vt, or yn can be written as fn x minus vt. So if we combine many such waves, f1 x minus vt plus f2 x minus vt plus dot 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 plus fn x minus vt, or we can write as some sigma I equal to 1 up to n fi x minus vt. So this is principle of superposition, right? Now here for simplicity we consider only two harmonic waves traveling on a stretched string, both with the same angular frequency and wave number k. So the wavelength will also be set. So here equations are given. One wave has equation y1 as a function of x and t, a sine kx minus omega t, and another wave y2 xt, a sine kx minus omega t plus phi. Now if the two waves superpose, in that case what happens? We write their equation as y xt equal to a sine kx minus omega t plus a sine kx minus omega t plus phi. Now if you remember the formula, sine a plus b, that is equal to sine a cos b plus cos a sine b, right? There is another formula. Here that formula we are going to apply sine c plus sine d. Sine c plus sine d means 2 sine c plus d by 2 cos c minus d by 2. So if we apply that formula, so this is c, this is d. So 2 sine c this kx minus omega t plus d kx minus omega t plus phi divided by 2 into cos c minus d. If you subtract the two, you will get minus pi, but minus pi by 2, but cos minus theta gives cos theta, that is why cos pi by 2. So we have got this equation. Now we can further simplify. So this becomes y xt 2a cos pi by 2. We write cos pi by 2 in the beginning, and then sine kx minus omega t plus pi by 2. This equation is also a harmonic traveling wave in the positive direction of x-axis with the same frequency and wavelength. However, its initial phase angle is pi by 2, right? Here it becomes pi by 2. The significant thing is that its amplitude is a function of the phase difference. Here amplitude changes. Earlier it was just a, now it becomes 2a cos pi by 2. Here the waves are given, and now new situation is also shown. The resultant of two harmonic waves of equal amplitude and wavelength according to the principle of superposition. The amplitude of the resultant wave depends on the phase difference phi, which is 0 for A and pi for second one. Both are in opposite phase, right? Here both waves move in the same phase. Now the same thing is being explained here. So A amplitude is 2a, as you have observed here, 2a cos pi by 2. Same thing we are taking here. So amplitude is a phi 2a cos pi by 2. If phi becomes 0, then what happens? You know, cos 0 degree is 0. So we will get this as just 2a. So our equation, this equation will become this thing, 2a cos, this becomes pi is 0, 0 means 1. So 2a sine kx minus omega t. only, because this pi is getting 0. So we have got this relation, right? The resultant wave has amplitude 2a. The largest possible value for a, this is largest possible value. For phi equal to pi, the waves are completely out of phase and the resultant wave has zero displacement everywhere at all times. As you can observe from here, the net effect will get cancelled. Now, equation 14.33, this equation refers to the so-called constructive interference of the two waves where the amplitudes add up in the resulting wave, and just opposite will also happen. In this case, this is case of destructive interference where the amplitude subtracts out in the resultant wave, right? So this is basic point. Now reflection of wave. When a wave reflects, then what happens? So if the boundary is rigid, the pulses or waves get reflected, and the phenomenon of echo is an example of reflection by rigid boundary. If the boundary is not completely rigid or is an interface between two different elastic media, the situation is somewhat complicated. A part of the incident wave is reflected and a part is transmitted into the second medium. If a wave is incident obliquely on the boundary between two different media, the transmitted wave is also called the refracted wave. So refraction also takes place. The incident and refracted waves obey Snell's law of refraction. I think you remember what is Snell's law. Sin I upon sin R equal to refractive index of the second medium. And the incident and reflected waves obey the usual laws of reflection. Then here, here pulse is shown, and this is a rigid wall. So from here it will get reflected and then it will have phase difference of pi, right? So this is basic point. Now if on the other hand the boundary point is not rigid, then what happens? So then phase difference will not be added, right? Here, to summarize, a traveling wave or a pulse suffers a phase change of pi on the reflection at a rigid boundary and no phase change on the reflection at an open boundary. This point you have to remember. If the boundary is rigid, in that case, there will be phase difference of pi after reflection. But if boundary is not rigid, in that case, no change in phase will occur. Here, equation, let the incident traveling wave is written like y2 function of xt a sine kx minus omega t. Now, as I told you that at a rigid boundary, there will be phase difference of pi. So we write the equation y reflected as a function of x and t a sine kx minus omega t plus pi. But sine pi plus theta gives minus sine theta because it will be in third quadrant. So in that case, we will get minus a sine kx minus omega t. So this is the case when boundary is rigid. Now at an open boundary, the reflected wave is given by, so nothing will happen, it will remain same. So clearly at the rigid boundary, what happens? The two, this result and this, if you find the sum, you will get 0. So that is why we say y equal to y2 plus y reflected gives 0, right? Now we are going to see standing wave, and then we will consider different modes of vibrations. So we consider above reflection at one boundary, but there are familiar situations like a string fixed at either end or an air column in a pipe with either end closed, in which reflection takes place at two or more boundaries. In a string, for example, a wave traveling in one direction will get reflected at one end, which in turn will travel and get reflected from the other end. This will go on until there is a steady wave pattern set up on the string. Such wave patterns are called standing waves or stationary waves. To see this mathematically, we consider a traveling wave along the positive direction of x-axis and a reflected wave of the same amplitude and wavelength in the negative direction of x-axis. So let's write the equations. So y1 xt a sine kx minus omega t. This is in positive x direction. Consider another wave in negative x direction. So it here there is positive sign. Y to xt equal to a sine kx plus omega t. Now we add the two. So according to superposition principle, we get y xt equal to y1 xt plus y2 xt. Now, so we write the equation A, we take out sine kx minus omega t plus sine kx plus omega t. And again, we are going to use the formula, this thing, sine, this sine c plus sine d. This is c, this is d. So we simplify, that gives 2 sine a cos b. So we get this relation, right? Note the important difference in the wave pattern described by previous equation and that described by this equation. So the term kx and omega t appear separately. Here they are appearing separately, but in previous case it was not separate. It was as a function, means as the argument of sine. Now, not in the combination kx minus omega. The amplitude of this wave is 2a sine kx. This all is amplitude. Thus, in this wave pattern, the amplitude varies from point to point, but each element of the string oscillates with the same angular frequency omega or time period. There is no phase difference between oscillations of different elements of the wave. The string as a whole vibrates in phase with differing amplitude at different points. The wave pattern is neither moving to the right nor to the left. Hence, they are called standing wave or stationary wave. Correct? Now, here we are going to discuss about the nodes and antinodes. So nodes and antinodes are the points where amplitude, nodes means amplitude is the least and antinode means amplitude is the largest. So we can see, suppose we take this point here, amplitude is largest, at this point amplitude is the least. So this will be node, this will be antinode. So that is shown here also. Now, you have understood, I think, node means here when there is no amplitude, means almost zero amplitude. Now we will see the condition. So let us determine these normal nodes for a stretched string fixed at both ends. So both ends are fixed. This is one end, this is another end. Now we are going to see the relation. So what we have observed, we have seen the relation here, like this relation yxt equal to 2a sine kx cos omega t. Now we are going to put 0 this thing and this thing separately. So first let's put kx, if sine kx equal to 0, this term. So if you remember, sine will become 0 at 0, pi, 2 pi, 3 pi. So we can write kx equal to n pi. So 0, where n is 0, 1, 2, 3. Or we know that k equal to 2 pi by lambda. So we write this value here, 2 pi by lambda, and then simplify. So we get value of x equal to n lambda by 2, where n can be 0, 1, 2, 3. So if we write here n equal to 1, you will get half of lambda. If you write 2, it will become lambda. So these are the positions where we get the least amplitude, right? And if you remember, least amplitude means it's a node. Now, to get position of antinodes, what do? We write it as maximum. So sine kx modulus value becomes 1. So what are the possible values of kx then? So kx must be equal to n plus half pi, where n can have any integral value like 0, 1, 2, 3. And as we know, k equal to 2 pi by lambda. So we write this value here. So after writing that, 2 pi by lambda here, and then we can simplify. So on simplification, we get x equal to n plus half lambda by 2, where n can have any value like 0, 1, 2, 3, etc. But they must be positive, right? So here again we get the position of antinodes. Now antinodes can be determined in terms of length. If you notice here, in this case. So here this is position of node, sorry, this is position of antinode. Here what is happening, this is fundamental or first harmonic between these two ends. Here this is equivalent to half wavelength. Here what is happening, in the same length this complete wave is formed. So this length of the string is equal to complete wavelength. Similarly, here 1.5 wave is formed in the same length. So L will be equal to 3 by 2 lambda. In this case, in next case, what you observe, there are two waves, one wavelength, then another wavelength, right? So two wavelengths are equal to L. In this case, 2.5 wavelengths, then this is three wavelengths. Here one wave, then this second wavelength, then third wavelength. So this here names are given: fundamental first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic, sixth harmonic, and so on. The same thing is explained here. If we see this condition here, in the case of stress string of length L fixed at both ends, taking one end to be at x equal to 0, here we take x equal to 0, here we take x equal to L, and then we see what is happening. So x equal to L, node condition requires that length L is related to lambda. So obviously L will be n times lambda by 2, where n can be 1, 2, 3. So when we write n equal to 1, we get L equal to lambda by 2. Means lambda should be equal to 12. So that is the case. This is just half of lambda. In length L, half of lambda occupies. Similarly, here the possible wavelengths of stationary waves are constrained by the relation lambda equal to, from here, 2L upon n. And frequencies, if we want to find out, V equal to nu lambda. So nu will be nV divided by 2L. So these are the relations. So harmonics, as I have already discussed, I think you have understood. Now we are going to see next situation. Here a glass tube partially filled with water illustrates this system. The end in contact with water is a node, while the open is an antinode. At the node, the pressure changes are the largest, while the displacement is minimum. At open end, what is happening? The antinode, it is just the other way, least pressure change and maximum amplitude of the displacement. So you have already understood that amplitude at the node is highest, at the node is least, and at the antinode it is the highest. Taking the end in contact with the water to be x equal to 0, the node condition we can again put. If the other end x equal to L, then antinode can be found. Antinode means maximum amplitude we are talking about. So in that case, the relation we can write like L equal to n plus half lambda by 2. We can put the values of n as 0, 1, 2, 3. So when we put 0, this becomes lambda by 4. It means to complete the wave, 4 times the length of the tube is needed, right? So the possible wavelengths are then restricted by the relation. We can write the value of lambda. So this 2L divided by n plus half, where n can have any value starting from 0. The normal modes, the natural frequencies of the system, frequency V equal to nu lambda. We can get the relation for nu equal to n plus half V upon 2L. Now, here the fundamental frequency corresponds to n equal to 0 and is given by, when we write n equal to 0, we will get V upon 4L. The higher frequencies are odd harmonics. So like we can write, here we have taken n equal to 0. If we write 1, then we will get 3 times V upon 4L, then 5 times V upon 4L, etc. That is why we say odd harmonics, right? Then here there is another condition, resonance conditions. If the external frequency is close to one of the natural frequencies, the system shows resonance. Normal modes of circular membrane rigidly clamped to the circumference, as in a tabla, are determined by the boundary conditions that no point on the circumference of the membrane vibrates. Now, we are going to see one important numerical here, and then we will apply the condition as we have already studied. A pipe 30 centimeter long, this is value of length, is open at both ends, which harmonic mode of the pipe resonates at 1.1 kilohertz source. Will resonance with the same source be observed if one end of the pipe is closed? Take the speed of sound in air as 330 meter per second. So first harmonic condition when pipe is open is nu one is v upon lambda 1, and we need 2L to cover 1 lambda, so v upon 2L, where L is length of the pipe. Now Vn, if we generalize, it becomes N V divided by 2L. Here just N is to be put. Now, first few modes on open pipe are shown in figure. We have already seen. Now, we can put the value of L as 30, and velocity of sound is given as 330 meter per second. So, after putting that value, we can generalize this. So, Vn equal to N times 330 divided by 0.6. That comes out to be 550 N times here hertz or per second. Now, we can put the value of N. Clearly, a source of frequency 1.1 kilohertz will resonate at V2. If you write here N equal to 2, what do you get? This will become nu 2. So 550 times 2, that will give 1100 hertz, which is equal to 1.1 kilohertz. So this is the second harmonic. Now, the situation is shown here. This is fundamental. This is second case in which here, so this is lambda by 4, this is 3 by 4 lambda, this is 5 by 4 lambda, so like this. Now here further situation is shown. So how many waves do you count here? One wave, and this is, so here is 7 by 2 lambda, this is 9 by 2 lambda, this is 11 by 2 lambda. Now, if one end of the pipe is closed, then another condition we are going to put. So frequency will be given by V upon lambda 1. 1/4 wave occupies in length L. So we write V divided by 4L, right? Now, in this case, what do we observe? We have seen that odd multiples of harmonics we get. So V3, 3V by 4L, V5, 5V by 4L, and so on. Again, we are going to put the value of L and V. After putting the values L equal to 30 centimeter, V equal to 330 meter per second, we can get the different frequencies like 275 hertz, and source frequency correspond to fourth harmonic. Since this harmonic is not possible mode, so no resonance will be obtained in this case. Now we are going to see what is beat. Beat means difference in frequencies. Beats is an interesting phenomena arising from interference of waves. When two harmonic sound waves are close but not equal frequencies are heard at the same time, we hear a sound of similar frequency, the average of the two close frequencies, but we hear something else also. We hear audibly distinct waxing and waning of the intensity of the sound. Waxing means increasing, waning means decreasing, with a frequency equal to the difference in the two close frequencies. As I told you, which means difference in frequencies. Artists use this phenomena often while tuning their instruments with each other. They go on tuning until their sensitive ears do not detect any beats. To see this mathematically, let us consider two harmonic sound waves of nearly equal angular frequencies omega 1 and omega 2 and fix the location to be x equal to 0 for convenience. Then the previous equation as we have seen, so here we are going to put phi equal to pi by 2. So S1, equation of displacement, S1 equal to A cos omega 1 t and S2 equal to A cos omega 2 t. Here we have replaced the symbol y by s. As you have already seen that we generally write equation y equal to A cos omega t. The same thing here, they are replaced by s is replaced by y, vice versa, y is replaced by s. Now, since we are referring to longitudinal not transverse displacement. Let omega 1 be the slightly greater of the two frequencies. So we are considering two here. There are two frequencies, omega 1 and omega 2. We are assuming that omega 1 is slightly greater than omega 2. The resultant displacement by the principle of superposition, we can add the two, S1 and S2. So S equal to S1 plus S2, A cos omega 1t plus cos omega 2t. Here A is taken common, and then we can use the formula cos C plus cos D. So that gives 2 cos C plus D by 2, cos C minus D by 2. So after putting the value, we get 2a cos omega 1 minus omega 2 t omega 2 t divided by 2 and cos omega 1 plus omega 2 t divided by 2. Now we can further write, here we are assuming this. So S equal to 2a cos omega bt cos omega at. Alright. So here if omega 1 minus omega 2 is less than omega and omega 2, then omega a will be greater than omega b. So we can write, the assumption is very simple. These terms are replaced by omega b and omega a. This thing omega a, this is omega b. So here some more information is given. Now if we assume omega 1 minus omega 2, this term is less than omega 1, then what happens? We can ignore this omega 2, which means omega a will be greater than omega a. We can interpret this equation. We are talking about this. We can interpret this equation as follows. The resultant wave is oscillating with the average angular frequency omega a. However, its amplitude is not constant in time. Unlike a pure harmonic wave, the amplitude is the largest when the term cos omega bt takes its limit from +1 to -1. In other words, the intensity of the resultant wave waxes and wanes with the frequency of 2 omega b, that is omega 1 minus omega 2 Now, since omega equal to 2 pi nu, the beat frequency will be given by nu beat equal to nu 1 minus nu 2. So you have understood how to find beat frequency. You will find the difference here. Diagrams are shown for the two cases. Superposition of two harmonic waves, one of frequency 11 Hz and the other of frequency 9 Hz, giving rise to beats of frequency 2 Hz. Of course, the difference of the two, this is 11, this is 9. Now, we are going to see question. Two sitar strings A and B playing the note dha are slightly out of tune and produce beats of frequency 5 Hz. So, it means they are differing by 5 Hz. The tension of the string B is slightly increased and the beat frequency is found to decrease to 3 Hz. What is the original frequency of B if the frequency of A is 4 to 7? So it is decreasing. So it's obvious it will be reduced by 5. So with what is the basic principle? Basic principle means when tension is slightly increased, then the frequency decreases. So here the same is given here. Increase in the tension of a string increases its frequency if the original frequency of B were greater than that of A. Further increase in nu B should have resulted in an increase in the beat frequency. But here just opposite thing is happening. Here it decreases to 3 Hz. Right? So definitely we have to reduce this value by 5 to get the frequency of B. So here the beat frequency is found to decrease. This shows that nu B is less than nu A. Since nu A minus nu B is given as 5 Hz because beat frequency means difference of the two frequencies. So V and VA is given 427 Hz. So of course VB will be 422 Hz. I think you have understood. Once again we can have a quick recap. Here frequency of A is 427 and what is happening? Here beat frequency is given as 5. It means the frequencies of the two VA and VB differ by 5. But whether frequency of B is less or more than that of A, so for this we just see we increase the tension, right? If on increasing the tension, beat frequency is decreasing, it means the frequency of A will be less than that. Sorry, frequency of B will be less than that of A. The same is happening, so we can get that frequency of V will be equal to 427 minus this frequency. This is just for checking that what is happening if tension is increasing. If tension, suppose reverse case if we consider, sorry, so in that case what will happen? Here if we increase the tension and the frequency is found to increase by 3, in that case the frequency of B will be 427 plus 5 Hz. So that is the basic concept. Now lesson is over. Let's have a quick recap of the lesson. Mechanical waves can exist in material media and are governed by Newton's laws. Transverse waves are waves in which the particles of the medium oscillate perpendicular to the direction of wave propagation. Longitudinal waves are waves in which the particles of the medium oscillate along the direction of wave propagation. Progressive waves is a wave that moves from from one point of medium to another. Then comes the displacement in sinusoidal wave propagating in positive x direction is given by y xt a sine kx minus omega t plus phi, where a is amplitude, k is propagation constant, omega is angular frequency, and this all kx minus omega t plus phi is the phase. Here phi is the phase constant or phase angle. Then wavelength lambda of a progressive wave is the distance between two consecutive points of the same phase at a given time. In a stationary wave, it is twice the distance between the two consecutive nodes or antinodes. Then time period t of oscillation of a wave is defined as the time any element of the medium takes to move through the complete oscillation. Through one complete oscillation, it is related by the angular frequency as t equal to 2 pi by omega. Or frequency we can say nu equal to omega upon 2 pi. We can find the speed of progressive wave by finding the ratio of omega upon k, that gives lambda upon t or lambda times nu. And then comes the speed of a transverse wave on a stretched string is given by v equal to t upon mu, where mu is mass per unit length. Then sound waves are longitudinal mechanical waves that can travel through solids, liquids or gases. The speed v of sound wave in a fluid having bulk modulus b and density rho is given by v equal to square root of bulk modulus divided by density. Right. The speed of longitudinal wave in a metallic bar is given by v equal to square root of Young modulus divided by density. And for gases, since b equal to gamma p, the speed of sound changes to v equal to gamma p divided by rho. This, if you remember, this is Laplace correction, because Newton gave this formula and this value, when we evaluated it, we got 280 meter per second. That was less from the practical value, because practical value is almost 330 meter per second. So when here Laplace suggested that the wave propagation is of adiabatic nature, then he introduced gamma. So after that we got around 330 meter per second. So that was correct value. Now next point is, when two or more waves traverse simultaneously in the same direction, the displacement of any element of the medium is the algebraic sum of the displacements due to each wave. This is known as principle of superposition of waves. So y can be written as sigma I up to n fi and then x minus vt. Now two sinusoidal waves on the same string exhibit interference, adding or cancelling according to the principle of superposition. If two waves are traveling in the same direction and have the same amplitude a and frequency but differ in phase by phase constant phi, the resultant is a single wave with same frequency omega, and its equation is y xt 2a cos 1 by 2 phi. This is amplitude sine kx minus omega t plus phi by 2. So here if phi we put 0, then this term will become 1, this term will cancel out, and then we will get simple equation. Then comes a traveling wave at a rigid boundary or a closed end is reflected with a phased reversal, but the reflection at an open boundary takes place without any phase change. For an incident wave, y1 yixt equal to a sine kx minus omega t. When it gets reflected from a rigid boundary, then addition of pi takes place. So that is why we can write it y reflected is minus a sine kx plus omega t, because sine pi plus theta gives minus sine theta. For reflection at an open boundary, nothing will happen, so it will remain. Just here, sign will change because wave will reverse its direction. The interference of two identical waves moving in opposite directions produce standing waves. For string with fixed ends, the standing waves is given by yxt 2a sine kx cos omega t. Here, this will be the amplitude. Now, standing waves are characterized by fixed locations of zero displacement called nodes and fixed locations of maximum displacement called antinodes. The separation between two consecutive nodes or antinode is always lambda by 2. A stretched string of length L fixed at both ends vibrates with frequencies given by nu equal to nv upon 12, where n can be written as 1, 2, 3. The set of frequencies given by the above relation are called the normal modes of oscillation of the system. The oscillation mode with the lowest frequency is called the fundamental mode or the first harmonic. The second harmonic is oscillation mode with n equal to 2 and so on. Then next point is a pipe of length L with one end closed and other end open, such as air column, vibrates with frequencies given by nu equal to n plus half v upon 12, where n can have any value in 0, 1, 2, 3, etc. The set of frequencies represented by the above relation are the normal modes of oscillation of such a system. The lowest frequency is given by v upon 4L, which is called fundamental mode or first harmonic, and a string of length L fixed at both ends or an air column closed at one end and open at the other end or open at both ends vibrates with certain frequencies called their normal modes. Each of these frequencies is a resonant frequency of the system. Now, last one is beats arise when two waves having slightly different frequencies, say nu1 and nu2, and comparable amplitudes are superposed. The beat frequency is given by nu beat equal to nu1 minus nu2. Now, here some more points are given. If you consider wavelength, distance between two consecutive points with the same phase, symbol is lambda, dimension is L, unit is meter, propagation constant K, which is 2 pi by lambda, unit is meter inverse, and dimension will be L minus 1. Then wave speed, V equal to nu lambda, and then beat frequency, we have studied that this is difference of the two frequencies, and there are certain points that we can consider. So here, let's read it, and after that relation will be over, and then we will start numericals. A wave is not motion of matter as a whole in a medium. A wave is not motion of matter as a whole in a medium. A wind is different from the sound waves in air. The former involves motion of air from one place to another. The latter involves compressions and rarefaction of the layers of air. In a wave, energy and not the matter is transferred from one point to another. Keep in mind, in a wave, energy and not the matter is transferred from one point to another. In a mechanical wave, energy transfer takes place because of the coupling through elastic forces between neighboring oscillating parts of the medium. In mechanical wave, energy transfer takes place because of the coupling through elastic forces between neighboring oscillating parts of the medium. And transverse waves can propagate only in medium with shear modulus of elasticity. You remember shear modulus when deforming force is applied? So we write deforming force divided by theta. Deformation produced means what angle it shifted, right? Longitudinal waves need bulk modulus of elasticity and are therefore possible in all media, solid, liquid and gases. In a harmonic progressive wave of a given frequency, all particles have the same amplitude but different phases at a given instant of time. In a stationary wave, all particles between two nodes have the same phase and a given instant but have different amplitude. And the last point is relative to an observer and rest in medium, the speed of a mechanical wave in that medium V depends only on elastic and other properties such as mass density of the medium. It does not depend on the velocity of the source. So these are main points that you have to keep in mind while solving the questions for competition, etc. I think you have understood the topic fully. Now we will do numericals based on these concepts in next lecture. Thank you for watching. Team Educate.